Every time you hold a stainless steel spoon or look at a gleaming skyscraper, you're looking at the end of a violent, energy-hungry journey. Traditionally, creating this metal requires temperatures hotter than volcanic lava just to coax the nickel out of its rocky prison. But on March 27, 2026, in the rugged terrain of Newfoundland, a discovery known as alloy max changed the rules of the game forever. Geologists found a massive deposit of Awaruite, a mineral that shouldn't really exist in these quantities. This isn't just another nickel mine. This is a discovery of a material that has already done the hardest part of the engineering for us, right inside the Earth's crust.
To understand why this is a big deal, we have to look at how we usually get nickel. Most of the world's nickel is trapped in sulfides or oxides, chemical cages that hold the metal tight. To break those cages, you have to roast the ore, releasing sulfur dioxide, and then smelt it at incredible heat. It is a multi-step, multi-billion-dollar bottleneck that consumes massive amounts of electricity. But Awaruite is different. It is a natural alloy of nickel and iron, specifically Ni₃Fe. It's already in a metallic state, meaning the Earth has already performed the smelting for us over millions of years. Awaruite forms through a process called serpentinization. When water hits specific types of iron and nickel-rich rocks deep underground, it triggers a chemical reaction that strips away the oxygen and sulfur. The result is a highly dense, incredibly pure metallic grain scattered throughout the rock. It's like finding a mountain made of pre-mixed ingredients for the world's most important steel. The Alloy Max discovery in Newfoundland revealed that these grains aren't just rare anomalies. They're part of a massive, accessible geological formation that could power the next century of industry. But there's a catch. Even though the metal is there, it's still locked inside billions of tons of waste rock. You can't just pick it out with your hands. This is where the mechanical engineering comes in. Engineers had to design a way to find these microscopic metallic needles in a haystack of granite and serpentine. The solution lies in two unique properties of Awaruite: its specific atomic lattice and its almost supernatural magnetism. These are the keys that unlock the Alloy Max treasure. In the next few minutes, we're going to dive into the atomic scale to see why this lattice is so stable, and then look at the massive machines that use magnetism to pull metal straight out of the ground. This isn't just a story about rocks, it's a story about how we can stop burning the planet to build our future. And it all starts with the way 3 nickel atoms hold on to 1 iron atom. Welcome to the engineering behind the most important material discovery of the decade. This is the science of Awaruite. At the heart of Awaruite is a specific atomic arrangement called a face-centered cubic lattice, or FCC. Imagine a cube where there's an atom at every corner and one right in the center of every face. In Awaruite, the nickel and iron atoms aren't just randomly mixed, they are ordered. This means they occupy very specific spots in that cube, creating a structure that is incredibly dense and resistant to corrosion. Because it's already in this metallic lattice, there is no oxygen or sulfur to remove. In a traditional refinery, you'd spend 70% of your energy just breaking those chemical bonds. Here, that work is already done. But the real superpower of Awaruite is its magnetism. Most nickel ores aren't magnetic at all, or only weakly so. Awaruite, however, is a ferromagnet, and a powerful one at that. It is roughly 10 times more magnetic than typical iron ore minerals like magnetite. This is because of the way the electrons in the nickel-iron lattice align their spins, creating a unified magnetic field. This extreme magnetism allows engineers to use a process called magnetic separation at a scale and efficiency never seen before in nickel mining. The mechanical separator drums used at the Newfoundland site are engineering marvels. These aren't your kitchen magnets. They are massive, rotating cylinders lined with high-intensity rare earth magnets. As the crushed rock slurry flows over these drums, the Awaruite grains are literally ripped out of the stream. The force is so strong that it can capture particles as small as 10 microns, thinner than a human hair. This mechanical process replaces the chemical-heavy flotation tanks used in traditional mines. No toxic chemicals, no massive tailing ponds, just the pure physics of magnetism. Once the Awaruite is captured, it forms a high-grade concentrate. Because it's already an alloy of nickel and iron, it's essentially a pre-concentrate for stainless steel. In a typical line, you'd have to ship a 15% nickel concentrate halfway across the world to a smelter. But the Alloy Max concentrate is so pure, it can bypass the smelter entirely. Think of it like being able to bake a cake by just picking the pre-mixed batter off a tree. You've skipped the milling, the mixing, and the mess.
This ordered atomic structure and the resulting magnetism aren't just curiosities. They are the foundation of a new industrial pathway. But the true genius is how this connects to the global steel market. By eliminating the smelting stage, we aren't just saving money. We're removing the single largest carbon bottleneck in the entire metal processing industry. Next, we'll see how this mine-to-stainless pathway is actually built and why Newfoundland is about to become the greenest metal hub on the planet. The traditional path to stainless steel is a logistical nightmare. You mine in one country, smelt in another, and refine in a third. Each step adds costs, energy, and massive CO2 emissions. The Newfoundland mine-to-stainless pathway collapses this entire chain. Because the Awaruite is already metallic, it can be fed directly into an electric arc furnace alongside iron scrap. This eliminates the roasting step entirely. In traditional nickel processing, roasting releases sulfur dioxide, which requires massive scrubbers to prevent acid rain. Awaruite has zero sulfur. No sulfur, no acid rain, no scrubbers. The energy savings are staggering. Smelting nickel is one of the most energy-intensive processes in human history. By skipping it, the Newfoundland project reduces the energy required per ton of nickel by nearly 60%. In a world trying to reach net zero, this isn't just an improvement, it's the only way forward. The Newfoundland site is powered by the province's vast hydroelectric grid, making it a near-zero carbon operation. This creates a green nickel premium. Companies like Tesla or Apple, who need massive amounts of nickel for batteries and frames, are looking for exactly this kind of low-carbon supply. But the impact goes beyond just carbon. This discovery changes the geopolitics of metal. Right now, nickel processing is heavily concentrated in just a few regions, often with lower environmental standards. By bringing high-grade nickel production to North America with a clean mechanical process, we are securing the supply chain for the electric revolution. It turns out that the solution to some of our biggest engineering challenges was hidden in the rocks of Newfoundland all along, waiting for us to understand its atomic secrets. As we look to the future, the Alloy Max discovery is a template. We are moving from brute force engineering, where we burn everything to get what we want, to elegant engineering, where we use the natural properties of materials. Awaruite is just the beginning. As our sensors get better and our understanding of material science deepens, we will find more of these geological shortcuts that nature has provided. The engineering of the future isn't about fighting nature, it's about partnering with it. It's about finding the atoms that are already doing the work and giving them a way to reach the surface. So, the next time you see a stainless steel bridge or a new electric car, remember the Awaruite of Newfoundland. Remember the 3 nickel atoms and their iron core, locked in a perfect magnetic dance. Because sometimes the most advanced technology in the world isn't something we built in a lab, it's something we found, buried deep in the earth, waiting for us to finally see it for what it truly is. A miracle of material science, hidden in plain sight. A gift from the earth that is helping us build a cleaner, stronger world, one atom at a time.